So now we're going to take a look at the extrema for functions of two variables, and this is going to be a little bit of an overlap with the first and second derivative test. So we're going to look at finding the absolute and relative extrema of a function of two variables, and we're going to use the second partials test to find the relative value. Remember, relative means that you could have more than one max or min, and it becomes relative, versus absolute means this is the actual highest point. So for absolute extrema and relative extrema, one way to visualize this is the image at the bottom corner. So obviously when we're working in functions of multiple variables, we're talking about three-dimensional objects like we graphed in week 1. So with this, we're going to consider that we have a continuous function of two variables like seen in the image, and it's defined on this region of R. So I'm looking at this bounded region with endpoints on each point of the thing. From there, I'm going to have a couple of assumptions like we always do. I'm going to say that there's values where there's a minimum and there's a maximum point. Because it's bounded, there would have to be a max and a min because it's bounded. So there's always going to be a highest point and a lowest point when we're talking about bounded things. So in here, we have for all the x and y values in this little blue plane, there is a max and a minimum in that region. So that's what that second piece means. So all we're saying is, just like if I had a parabola and I was limiting the domain to 2 and 4, there'd be a highest value and there'd be a lowest value because I'm limiting the domain. That's the concept we're trying to think through here. So a region in the plane is closed if it contains all of its boundary points, which means that if the circles are colored in. So if you remember back in Calculus 1, we said, oh, if the circles are colored in, then it's closed, it's included. Same thing in a region of a plane if it contains all of its boundary points. If that's true, then that's a good thing. That helps us to get the relative extrema. The extreme value theorem says with the region, it's both closed and bounded. So it's bounded if it's a subregion of the disk in the plane. So all that means to say is that this extends on. It's not just this actual piece if I'm describing the function, but I'm just looking at a piece of this, not the entire thing. That's what we're saying when we're saying it's bounded. It's just like in the domain when you limit the domain. Absolute extrema and regulative extrema have a couple of things with the extreme value theorem. There's one point that's the lowest, one point is the highest. So it's going to match everything we know from Calculus 1, except for now we're saying that it's in the xy plane. A minimum is the absolute minimum if it is the actual lowest point, meaning it has the smallest y value. It's an absolute maximum if it's the highest point, meaning it has the actual highest y value if I'm in Calculus 1. Here, because I'm working with multivariable calculus, it's not just a y value, it's the actual extrema of the plane itself. So here, look at this, maximum point is at the height of this curve of the plane, and then same thing, minimum is going to be at the lowest point in that curve in the plane. So if I have to have an absolute if it's bounded. That's a given. But I could have additional extrema that are going to be relative. So I could have multiple waves. So think about it like an ocean wave. And those waves could all have different heights. So that's what we're talking about here. So to say that a function has a relative maximum means that there's a point that it's at least as high as all the nearby points. See these wave functions? Each peak of that wave is a relative extrema. It's relative to what's around it. There is an actual highest point. So to locate the relative extrema of f, I can investigate the points with the gradient of f is at 0, or the points at which one of the partial derivatives does not exist. So this is the same thing we did in Calculus 1. We set the function equal to 0, and then we would solve that for x, and we would also add in any points that were discontinuities. So that's the critical points, same concept as Calculus 1. Now, same thing, I'm going to look at the critical point by taking those partial derivatives, setting those equal to 0, and then again checking at any discontinuity that occurs. If something is differentiable, that means that I have component vectors that describe the plane. If I have component vectors, then every direction the derivative goes in must be 0 in those components so that I have a horizontal tangent of the plane. Okay, stop and think about that. Basically here is we're saying here is this blue, here's this function, and instead of finding a tangent line or a horizontal tangent line, I have a tangent plane. So this is the difference in multivariable and calculus 1. Here I have an entire plane that has a horizontal tangent, so it touches my graph at exactly 1 point. It appears such a point is likely the location of a relative extrema. So if that horizontal thing is happening, it's probably either relative or absolute. So what does this actually look like in practice? Okay, so we're going to work with the function we've kind of seen before. We're going to start by finding the critical points. So we're going to differentiate x while holding y as a constant. If y is a constant, the derivative of 2x squared is 4x. The derivative of y squared is 0. The derivative of 8x is 8. Minus 6y, derivative is 0. And plus 20, derivative is 0. So that's the partial with respect to x. Now I have a line, so it's really nice to set that line equal to 0. If I differentiate now with x is my constant, I would have 2x squared, the derivative is 0. Y squared, the derivative is 2y. 8x, derivative is 0. Minus 6y, derivative is negative 6. And then derivative of 20 is 0. So now I have two partial derivatives. I look at these partial derivatives, they're continuous everywhere. So the only critical points then are the places where these partial derivatives are equal to 0. And the beautiful thing about this is they're simple to solve, right? So I get the critical point, I get negative 2 when I solve the first partial, and I get 3 when I solve 2y minus 6. So my actual critical point is negative 2 comma 3. So how do I get to somewhere where I'm looking at this plane? Well, I'm going to go back here, and I'm going to take x and y, and I'm going to substitute for x and y. So that by completing the square, I can conclude that xy does not equal negative 2, 3. So there's a relative minimum. So if there's a relative minimum, I'm trying to take those critical points. So the critical point is negative 2. So where I see an x squared, I make it x plus 2. That's where the x plus 2 comes from. If it's 3, I make it a y minus 3, and I square it. And so if that is greater than 3, then I conclude that I have that. So the value of the relative minimum would be negative 2, 3 equals 3, as shown there in the graph. For the second partials test, this is going to be to find a relative extrema. I only need to look at the critical points. So some of these critical points yield what we call saddle points, which are not relative maxima or minima. This is where you have to really be careful. It's possible by utilizing this test that you may not actually get what you need. An example of this would be the given graph, because if I consider this surface that I'm looking at, it's not actually a maximum or minimum that's really happening if I'm thinking about this as a surface. So at the point 0, 0, both partial derivatives meet the criteria where the derivatives are 0. But if I'm looking at 0, 0, it's this weird, like, sudden change. So if you think about calculus 1, when they have those rapid pivots and corners, it doesn't work. The same thing is true here. That corner does not work. So we're going to call that a saddle point. So a saddle point means it satisfies the algebraic criteria, but it's not actually that. So if I have the second partials test, this looks just like calculus 1. If it's greater than 0 and then my function is greater than 0, it's a minimum. If it's greater than 0 and less than 0, it's a maximum. And if d is just less than 0, but the function is just a number, then it's what we call a saddle point. And then if d is 0, it's inconclusive. So here's another example. We're going to find a relative extrema. We're going to use the partial derivative process to get here and here. Those are easy to solve. I'm going to be able to set those equal to y. And so the critical points are going to occur when that's set equal to 0. Once I solve it for 0, I'm going to get the following values for two solutions. For y and x are 0 and y and x are 4/3. Because when I look at those partials and I get the zeros in there, I'm going to plug in 0 and I get -16, which is going to be less than 0. So because I have -16 that is less than 0, and then I have the partials test, I can conclude that at 0, 0, I have a saddle point. So that's where that's coming from. Furthermore, then I have that 4/3 to examine what's going on at 4/3, because I saw when x and y is 4/3, I have something else. So I'm going to plug that in, and I get the number +16, which is greater than 0. So I have one that's less than 0, one that's greater than 0, which means that I have a relative max that's happening. And that's going to be because when I plug it into the x side, -8 is less than 0. So the second partials test means things can happen in two ways. Something can look like a relative extrema, but it's actually a saddle point. So we've got to check those intervals there.